Hello, in this video we will talk about ionic bonds, talk about how to put together formulas for ionic compounds, and how to identify charges for transition metal ions. So we start with an observation. If you make a solution of sodium chloride on the left, that solution conducts electricity, whereas if you make a solution of sucrose, which is table sugar, that solution does not conduct electricity. There's some other differences between ionic and covalent compounds. Sodium chloride being an ionic compound, sucrose being a covalent or a molecular compound. When you look at the solid form, the molecular structure is different. When you look at what they do in solution, it's different. If you look at their melting point, it's different. So why? Turns out that ionic compounds exist in this three-dimensional lattice shape. So let's back up a step and say, what is an ionic compound? It's two ions of opposite charges that are held together by electrostatic interaction. And so when we say electrostatic interaction, it's the same physical interaction that you feel when you take off a shirt and it's staticky, or when you scuff your feet on the carpet and touch the doorknob. That is electrostatics. From your clothing, you may have noticed that things tend to cling together if they have opposite charges, and the same is true if you have positive and negative ions. So in the solid form, these atoms exist in a rigid repeating three-dimensional lattice, where you have various structures depending on the ion. In the case of sodium chloride, you have this very simple cubic structure where they occupy alternate vertices of cubes attached to each other. So we call this an ionic bond, and you're pairing together a cation and an anion. The cation is usually a metal, the anion is usually a nonmetal, or a group of nonmetals that together function as an ion. Those are called polyatomic ions, and we discussed those in chapter 10. So some examples: sodium chloride, lithium fluoride, and we generally call any ionic compound a salt. Your cation can be this giant protein molecule, and your anion can be this tiny little chloride, and we call that a salt. In contrast, molecules are all nonmetals, or metalloids, and they consist of two or more than two atoms, and there's a bunch of examples here, and they have very different properties, right? They're isolated molecules that in the solid state will come together and form some sort of crystal structure, but it's nothing like the alternating charge crystal structure of an ionic compound. So, what happens when you dissolve these things in water? So covalent compounds exist in water as neutral molecules. And so in the diagram here, here's methanol, and if you look over on the other side, when they're dissolved in solution, the methanol molecules are still in their same arrangement as they were before. They're effectively unchanged, they're just now in the water. Contrast this with ionic compounds. When an ionic compound dissolves in water, it dissociates into positive and negative ions. And so this picture is showing the solid cube of sodium chloride dissolve into the various ions that are attracted by different parts of the water molecules, depending on whether they're positive or negative. But overall, this shows us a very different behavior. So these positive and negative ions will work to conduct electricity. So if you have your electric circuit set up, where your battery or other direct current source are pushing electrons into the cathode, then the ions in solution can move across the solution to help transfer this charge. So when you have an electric current that's flowing, it's ultimately just electrons traveling through a wire. And so when you try to go across a solution, you need some sort of charge species to be able to also transfer that charge across the solution. In this case, the negative anions will move to the left, the positive cations move to the right, and it moves the charge across the solution, which then gets picked up by the anode and goes back out to your battery or power source. So, this is why ionic solutions can conduct electricity, whereas molecular solutions, it's not a charged particle in solution, and so it cannot conduct electricity in this manner. Okay, so having learned something fundamental about ionic compounds, let's talk a little more about what ionic compounds are, how they're put together, and things like that. So we'll use sodium chloride as our example again. So when you make a reaction that forms sodium chloride, say you take sodium metal, and here's the electron configuration of sodium metal. There's the stable electron configuration of neon, and then 1 electron in the 3s. And then chlorine has the electron configuration of neon, 2 in the 3s, and then 5 in the 3p. So this 3s electron in sodium is very reactive because once it disappears, then sodium has the stable electron configuration of a noble gas. And then this 3p5 is also very reactive because it just needs to add 1 more electron to get to 3p6 to have the stable electron configuration of a noble gas. This reaction is very likely to happen because it makes both these elements much happier, if you can characterize elements as being happy or sad. Okay, so during this reaction, an electron is transferred. An electron goes from the sodium to the chlorine. It makes a positive sodium ion because it lost an electron, and it makes a negative chloride ion because that gained an electron. Now, you have the positive sodium and the negative chloride, and they attract each other with an electrostatic force, and this creates the ionic bond and makes sodium chloride. So something we do in this chapter is we will write Lewis electron dot formulas to describe ionic reactions because it's a good introduction to Lewis formulas, which we then use extensively in the next 3 chapters. Also, this is a good model for explaining what happens in a reaction between a metal and a nonmetal to make an ionic bond. So here's what we do here. The Lewis dot symbol is defined as the symbol of an element where you make a dot around the element to represent each valence electron. So for example, hydrogen only has 1 valence electron. So you write hydrogen and you put a dot around it. The same is true for lithium or sodium, because remember, valence electrons are electrons in the outermost shell, and so you just look at that. Magnesium will have 2 valence electrons, so it gets 2 dots on there. Helium also has 2 valence electrons, so it has 2 dots. Nitrogen has 5 valence electrons, so it will get 5 dots around it, and so on and so forth. Carbon has 4, oxygen 6, fluorine 7. Any noble gas below helium will have 8 dots around it. Now, an artistic thing for how we place the dots is you'll write the elemental symbol, and then imagine around it you had a box. And then on that lines of the box, you put your electrons. And then there's some style as to whether you pair them or whether you leave them single that will make more sense once you understand the implications of that. But typically we'll pair the electrons. Nitrogen's kind of an exception here because nitrogen, when it makes compounds, it will typically make 3 bonds to other elements, and then it'll have a lone pair left over. So that's just why we're drawing nitrogen this way. You don't have a way to know that yet, but at least I can say that's why we're drawing the nitrogen this way. So then using Lewis dot structures to look at the formation of sodium chloride, sodium has this 1 valence electron, chlorine has 7, so this electron on sodium transfers over to the chlorine, and so then afterwards you're left with sodium with no valence electrons, and chlorine with 8. Now, you could make the argument that once sodium loses that outermost electron, it now has the valence electrons from the shell below it, the 8 valence electrons that would be left over. But we typically don't write it that way, because we're trying to show something. This is using chemical symbols as a language, and languages have intent and meaning in what you're trying to discuss. So we're trying to discuss that sodium loses an electron, and that'd be confusing if sodium went from 1 electron to 8 electrons in that process. So we just leave it this way. Sodium loses an electron and it's left with no valence electrons. Now don't forget the positive charge for the sodium and the negative charge for the chlorine. And voila, both atoms have the stable electron configuration of a noble gas. Okay, for another example, if magnesium and chlorine come together to make an ionic compound, what happens? Well, let's draw their dot structures. So magnesium, if you look on the periodic table, it has 2 valence electrons, so we'll draw them. I just picked the top. I could have picked the side, wherever, as long as you have 2 of them. And then you're going to add to it 2 chlorine atoms. Now each chlorine atom will have 7 valence electrons. And then after the reaction, well, now the magnesium is left with no valence electrons, and since you lost 2 electrons, it becomes a 2 plus ion. Now your chlorine, each one of those gains an electron and is left with 8 valence electrons. And that's how you would do this problem. Now the charge on each ion determines the composition of the compound. So the fact that magnesium binds with 2 chlorines to make this ionic compound is driven entirely by the fact that magnesium has 2 valence electrons and forms a 2 plus ion. Since magnesium makes this 2 plus ion, it needs 2 chlorines to reach a neutral compound, because each chlorine is only -1. So this leads us to the importance of being able to predict charges, because eventually we want to be able to predict how ionic compounds will go together, so we need to know charges of things first. So fortunately, this is relatively straightforward. You look at the periodic table, and if it has 1 valence electron, so this first column over here, it's going to lose that valence electron, because when it does, it reaches the stable electron configuration of a noble gas, which is what it wants to do. So the farthest left column, the alkali metals, will lose 1 electron to become a +1 ion. By the same logic, the alkaline earth metals will lose 2 electrons to become +2. Then it turns out that scandium, yttrium, and you could write aluminum over here if you wanted. They will all lose 3 electrons and become a 3 plus ion. Now on the other side of the periodic table, the fluorine will gain an electron to reach the electron configuration of a noble gas, and so will the rest of the halogens over here. The next group over with oxygen in it will gain 2 electrons to reach the electron configuration of a noble gas, and then nitrogen and phosphorus will gain 3 electrons. So you can just kind of look at the periodic table and say 1, 2, +1 and 2 from the left, and +3 here. And then from the right, -1, -2, -3. Easy. Just another thing you have to remember, but it's a really useful thing, because we need to know the predicted charges, which come from valence electrons, in order to figure out how to piece these compounds together. So let's show an example. So say you're trying to find the formula for an ionic compound between calcium and fluorine. Remember, this is named calcium fluoride. There's no di or tri or prefixes in here because it's an ionic compound and you don't use the prefixes. So if someone says calcium fluoride, you need to figure out what that is to write the formula. So first stop, charges. Calcium is a 2 plus because that's where it sits on the periodic table. And fluorine is a -1 because of the previous slide, how it sits on the periodic table. Now, okay, how do we combine these together in order to equalize the charges? One way you can do it is just look at this and say, well, I need 2 fluoride anions in order to equalize the +2 from the calcium cation. Another way you can do it is to do this little cross charges trick. So you take the +2 from the calcium and the negative from the fluorine. This is a -1 from the fluorine. And then the fluorine charge becomes the number of the calciums, and the calcium charge becomes the number of the fluorines. Either one of these works. It gives you the same answer. And double check your work too, that the total charge must be neutral. So if you take 1 calcium atom and it's a +2, great. If you take your 2 fluorine atoms and each one's a -1, that makes -2, and that adds to 0, because ionic compounds come together in such a way that ultimately neutralizes the charge. Okay, a couple examples. Pause the video, give them a try, and then start the video again for an explanation. Okay, so what's the formula for magnesium nitride? From the periodic table, magnesium sits here, where it's 2 plus, nitrogen sits here, where it's 3 minus. And so when these come together, if you do the cross charges thing, you'd see that magnesium 3N2 is what you'd get. And now if you think about it, alright, each magnesium is 2 plus, so 3 of them is going to make a total of +6 from the cation side. And then if each nitrogen is -3 and you have 2 of them, that makes -6, and that's going to add to 0. Perfect. So now calcium and oxygen come together. Well, how do they do that? Calcium oxide. Each one is +2, so if you do the cross charges thing, you'd get Ca2O2. But that's not a correct answer because we have a convention that we always write the subscripts in the most reduced form possible. So don't write Ca2O2, you would write CaO for calcium oxide. Okay, so now you've seen the importance of knowing the charges of certain ions, and it's fairly straightforward to figure out for the ones on this table like this that are pretty close to the edges. But what about the transition metals in the middle? In order for the transition metals to meet a noble gas electron configuration, they would have to lose far too many electrons to be feasible. So instead they do something else. You don't need to know this detail, but I'm going to say that some elements will lose electrons to reach an 18 outer electron configuration, because that has a relationship to shell structure that is useful. Other elements will lose electrons to obtain full subshells. So indium might lose the 5p electron in order to obtain a full subshell of 5s2 and 4d10. Ultimately, you don't know. And so with experience you can learn the charges that transition metals typically take, but more likely you'll just look them up. So your periodic table inside the front cover of your book includes common charges, listed in the columns right here. And so you can just go there as a reference. So here's the deal you need to know. So some metals will only take one possible charge, and some metals can take more than one possible charge, depending on which metal you have. And you need to know which ones are which. Why? Because they are named differently, and so in order to use the correct naming system, you have to know which one is which. The reason why they're named differently will make sense when we do naming in the next video. But for now, the short answer is that it has to do with possible arrangements you can have. Sodium and chloride are only going together in a 1-to-1 ratio because they won't take different charges, whereas iron and chloride can go together in 2 different ratios depending on whether the iron is +2 or +3, and those are different compounds, and we need to be able to name them differently. Okay, so the take-home message is this. Know that the elements listed in the table below have only one charge, and be able to deduce what that charge is, and then assume that everything else can take multiple charges. This gets you pretty close to the actual truth, and this is the line I'm going to take in this class. So looking at this table again, you have the ones that are within 3 columns of the edges, and then you have these ones right here. Zinc is going to drop 2 electrons to reach the electron configuration with a completely full 3D subshell, and so will cadmium. And silver will do a similar thing. It'll drop 1 electron to completely fill its 4D subshell. Sorry. It drops those electrons out of the s orbitals, and we'll talk about that in the next video also. So that's what we have for now. Thanks for watching. See you soon.